Hello, everyone. So today's lecture is a bit somehow out of the context of residential construction, but it's something that I'd really like to give as a lecture because this is more or less research coming from the last 8 to 10 years of my own research and research I've seen and studied worldwide. So the idea is that we're talking about form-resistant structures, so structures which are so thin because they have a specific structural form. They're generally called shells, or when they're made of discrete elements, they're called grid shells. There is a book which the title is The Art of Structural Engineering. You see it here on the right, and it's about the work of Jörg Schleich, a German engineer, but there are several others, such as Frei Otto. And you see this book here at the bottom called Grid Shells, or Gitterschalen. This was the first time the term was used in this way. And it comes from 1974. That's a journal. It's a journal of a department. It's like, let's say, the journal of the MSD, but it's the journal of the Institute for Lightweight Structures in Stuttgart. Every year they release, or they used to release, this journal. Now what they do, they build a research pavilion every year. But they're actually books, so they are so full of information, and they collect all the research they've worked on that specific year. And I highly suggest this as a reference. You won't find it at the library, so what I'll do, I'll probably upload it. I'll upload a few pages I've scanned so that you can flip through and see a lot of images. Another thing that I recommend is this lecture on the right, Learning from the Gothic Master Builders. It's not a book, but you can Google that and you'll find it on YouTube. It's a lecture, about an hour, a presentation of a colleague of mine, Dr. Philip Bloch at the ETH in Zurich. I highly recommend that because it's about masonry and stone construction, but in the shape of vaults and shells. He's a young guy, and he has done that for the last 10 years, first at MIT and then at the ETH in Zurich. Another interesting book, which you find probably at the library, and I'll try to upload something in PDF if I can, if I'm allowed to do that, Shell Structures for Architecture. You'll find several chapters in which there is a little bit of an overview. It's very difficult to find a book that collects all the information about this topic, but this book tries to do that, and it was just released in 2014, so you'll find everything about concrete, steel, timber, and masonry on this topic. In some chapters it's a bit more technical, but you know, it's done for both architects and engineers. The other book in the middle, Grid Shell, this is an Italian book because most of the research done on the timber construction actually comes from Italy. It's not translated, but again, I'll try to see if I can upload some images so that at least you see a few pictures. And somehow I have collected this information in this lecture, so you'll find them here anyway. Hello. Construction analysis, is that fine? Yeah. Okay, so what we'll cover today, first I'll try to tell you, there is not a very simple and easy definition of what a shell is or what a grid shell is. We should go more technical if we want to understand that, but I'll try to give you a couple of examples. Then after that, I'm going to talk to you about the techniques we use to find that shape, or we could say design that shape. And there are 3-4 techniques, or a mix of them. Generally, reverse hanging method, the minimal surface, pneumatic forms, analytical surfaces. Then we'll talk about the discrete version of shells, so steel grid shells and timber grid shells. They look very similar, but there are consistent differences in the way they are designed and built. So I'm going to show you both of them. I'm more into steel and glass, and actually a colleague of mine, which then became my wife, she's into the timber one. So at the end, I knew both of them, and I'll try to show you both things. So what I'm going to show you is part my work and part her work. Optimization is after the break. So what I'm going to do is to show what happens when you have free-form structures. Imagine some of the projects by Arata Isozaki, Toyo Ito, Zaha Hadid. In some of those cases, you won't be able to apply form finding. So what you'll do, you go through mathematical optimization to improve some specific performance. All right? And then I'm going to show you a few images of the design studio, how virtual becomes real, which is studio at the MSD, not running this semester, but it will run again next semester, of which I'm the studio leader together with another architect from the UK. And what we'll do, we try to put this topic into a design studio. So you can see what your colleagues, probably 2-3 years older than you, are doing at the master's level. So what is a shell? It's interesting to notice that I found in a book about Australian Aboriginals this type of constructions. So this idea is that you just bend some pieces of timber and then you clad them. So somehow you are creating a structure. Nowadays we would say this is called active bending. So it's resisting and it's taking a specific form because we bend that shape, and all of them together they create a dome, which is rather thin compared to a normal beam. We should imagine a joist of the houses you are studying. The thickness of this joist is rather consistent. But what happens in this case? You see that these elements are so thin because somehow the forces are distributed along the elements and there is never bending. So the idea, in order to decrease the thickness of structures, is to avoid bending. The only way to resist bending, I found this by chance, you probably know that, it's definitely a good example. In this case, the thickness is very reduced, so it's easy for me to bend this without breaking it. But if I flip it vertically, so in this case, I feel it's much more resistant because it can actually, this thickness resists to bending. But if I'm able to put this into the shape of an arch, then all the forces are transferred along that surface. So it's like saying that the thickness becomes this one. So you can go thin. All right? So that's the overall principle. And generally, we could say that eggs are a very good example of continuous shells. So that's why they're very thin and they've got that shape. And the behavior we're talking about is called membrane action. Membrane, again, just to give the idea of how thin these structures are. There is one point. These type of structures are not transparent. So we've got the idea is that they cover large spans, but at the same time, what's the point if we cannot bring light in? So there was another type of structures which was developed more or less at the same time, and it's called grit shells. So it means that they are made of discrete elements so that you can actually cover them with glass or a membrane or fabric so that the light can pass through. But they are actually very similar. So the behavior is always membrane action. They are in the family of form-resistant structures, and they are shells or grit shells. I'm proposing you this book, Structure in Nature is a Strategy for Design. Why that? Because somehow in this type of structures, nothing is lacking and nothing is superfluous. So somehow they are minimal, they're essential. And this happens also in a lot of natural forms. Fry Otto, who is one of the most important engineers and architects of this kind, he did a lot of research about nature and architecture, so architecture inspired by nature. But not just in terms of form, but in terms of form and structure. And in this book you'll find so many images of how nature can actually take advantage of some specific structural typologies to develop form. But this is the state of the art of shells. So we are in the 60s, and this is the Bern Zurich motorway. So you go to the service station, and you will see these two shells. I mean, you immediately see, look at the size of the car, and look at the span of this shell. Would you like to guess what's the thickness of this structure? I can tell you there are two different thicknesses. One is here, and one is at the base, just to avoid a little bit of buckling. At the base we're talking of about 30 centimeters, but here we're talking of less than 10 centimeters. So it's very thin. I don't even know exactly how they could pour that in, so we're talking about that. But it's because, you know, it's like the three-dimensional version of an arch. Let's say that. We could say this three-dimensional version of an arch, because all the forces can actually be transferred within that thickness. If there is any bending or if load is applied in a way that is not, you know, the vertical one or normal to the surface, then we're going to have a problem, because then there will be bending. Another example is this one, a bit thicker, but the point is that the previous one was a triangle, and this one is again another triangle. So there are 1, 2, and 3 supports, but there are cantilevers. So in this case, you see the thickness has been highly increased, and I think you can perceive that. So architecturally, you see this is much heavier, all right? But also a little bit of cantilever is possible in some cases, and this is a bad example of architecture because it was developed in the 60s just as a shell, and the idea of shells is always the large span. So the idea is that the space underneath is without intermediate supports. I don't want columns, I don't want extra elements. I just want to be free to place whatever I want. That's why it's generally used for stadiums or train stations. You generally find this type of topologies in these type of structures. So what they did, they decided, why don't we put Oki underneath? So they did a stadium underneath, and destroying entirely the idea of the large span and the big space. So somehow, the way they have redone this project in the early 2000s is not really thinking about what was the origin of this project. I mean, my feeling is that I always want to get rid of the roof and make another one, because it's like, it doesn't fit. But the interesting part comes now. So it's form finding. Now you wonder, how can you draw these shapes, and how can you make sure that these shapes are actually good in structural terms? Well, you do that through a few techniques, and the first of these is form finding. So form finding is not something that you have to use in its broad meaning. So if you're designing your own house and you're unsure about the roof and you are doing some experiments, you could say, I'm doing a little bit of form finding. No, you can call that form making, but it's not form finding. Form finding refers to structural design, all right? So it's a matter of finding what the optimal shape is. So never say when you are designing and doing experimentations in your own studio, I'm doing form finding. Form finding is when you design a shell or a grid shell. That's form finding. It's a technical term. So optimal shapes. Why that? Because we're finding just one optimal. There is only one optimal, and we're going to find it. And the way we do it is using experimental tools. So physical models in structural engineering are called experimental tools or techniques. And when we talk about digital tools, they are called numerical. All right? So it's experimental, physical, numerical, digital. So that's the terminology. Bear in mind this definition. So what happens, that's the simplest way to do it. This is a photo I took in Denmark. A student of mine did this model. So you just take some clips, and when you connect them together, you see there is no rotational stiffness, so they can actually rotate. So if you just leave them under gravity load, they will take the shape of an arch. That shape is a shape in a state of pure tension. So what you do, you take a picture, mirror it, and you get the compression-only situation. So if you mirror that, you actually get the shape of a shell. Of course, you need to be a little bit more precise than that. This is a little bit imprecise. But if you do the model properly, you can simulate with a physical model a structural property. What you need to do, you can't do a model just using this. You need to connect this one with another one, making sure that there is no rotational stiffness, so that the elements are able to rotate. In that case, you get the state of pure tension. And the Sagrada Familia in Barcelona, I don't know how many of you have been there, but Gaudí designed this building using exactly these techniques. So what he did is use a set of wires and sandbags to make sure, so you see these are the sandbags, and actually the model is this one on the right, and this is already the mirrored version. And these are a set of discrete wires that tend to define the the shape of that cathedral. And what was the challenge for Gaudi? The challenge was to try to do something better than the Gothics. You know that Gothic architecture is all about structure. So there is structure and then cladding. And in this case, what he wanted to do is that now we have got tools to design structures in order to understand exactly where the forces are. So what I'll do a challenge. So I'll do the biggest and the tallest cathedral in the world, which isn't finished yet, but apart from that, that was the idea. Through form finding, I can do a building out of stone and make sure that it's the tallest and the biggest ever done. So this model is not the original one. Unfortunately, the original one doesn't exist anymore, but it was reconstructed by Fray Otto in 1974. So the model you see here is now exposed in Barcelona, but it was redone in 1974, and it actually is the evidence of the work by Gaudi. You know, when you take a photo, then you invert it, and then you can draw on it. So you design over the drawing. But again, you need to be precise. They needed, I think they took more than 6 months to build this model. You know, make sure that everything is done precisely. Because, for instance, I did this exercise with the students, and generally what you get within a week is this type of models. And you see both in elevation and plan view that the level of precision is not enough to design. So, for instance, these are all supposed to be symmetric structures, but some other not, because a small mistake means that your design is compromised. So precision is the key if you perform fault finding by means of a physical model. All right? Of course, you don't need to do that just with a chain or ropes. In that case, you would get a catenary shape. So catenary comes from the Latin catena, which means chain. So remember that name, catenary. In the two directions, so as a two-dimensional structure, we get a shell, or we get a membrane. Okay, catenary. And in the 3D space, we could call, let me go back, we could call this a funicular structure. Funicular. So which means a set of catenaries in the 3D space. And when it's continuous like that, we can call it a shell or a membrane. So these are the technical terms. It's a bit difficult, I know, it'll take a while to get into that. But how do you get this model? Yeah, of course, you can discretize it in a set of catenaries, but you can also do another thing. You can hang a piece of fabric, make sure there is proper, dead load on it, and then you freeze it. And that's the shape you get. This is something that another Swiss engineer discovered just one morning. It was freezing outside in Switzerland in winter. So what he did, he probably washed some clothes and hung them outside, outdoor. In the morning, he found them frozen. And they were in this type of shapes. So he decided to invert them, and he found out that they were actually the shapes of shells. So that's the way he started designing these. And this is a physical model of the open-air theater you see down here. So again, we're talking about a minimum amount of material used in the shell. So pieces of fabric are used to do that. And again, I've done the same experiment with the students. And what we are in Denmark here, so it's about 5 years ago. So what you see is that you generally take a sheet of perspex so that you can just puncture it with a grid. You make a set of holes and you generate a grid so that you see this table here. You define where are the suspension points, so the support points, and you play with them so that you can define a family of shapes, a family of possible solutions. The ones you see here on the top, they are called boundary conditions. The ones you see at the bottom, they're called solutions. From some specific boundary conditions, we get other solutions. But we are always constrained within a certain family of solutions. So this is at the same time the fascinating part, but also the limit. So you see how you are limited in designing. And this is the way you can actually do that physically. So why are these things of interest? well, these things are of interest because we can talk about concrete architecture, steel, timber, but also masonry. In the third world, in Africa, these type of constructions are highly used because they can get clay and they make their own bricks. And this structure here has been done entirely out of that. So the idea of using shells to develop masonry and stone construction, especially in Africa or maybe South America, is still diffused. It can be, it can be a topic of research in order to make very cheap and at the same time efficient and also beautiful constructions, because the idea of the light, but at the same time to protect yourself from the sun, is of major importance over there. If you watch the lecture that I proposed to you at the beginning, one of the first slides, you'll see that this example, specifically this example, is explained in detail. All right, there is another way to find structural form. That was called the reverse hanging method. And now we're going to the second one. The second one is called minimal surface. If you hang a piece of fabric, you will never find this shape. But you will find this shape if you use the principle of the minimal surface. This is a bridge done in 1971, south of Italy. It's a bridge over the Basento River. And what happens in this case is that you can design it using soap bubbles. So you define, let's say you take a steel frame, a steel wire, and you define the boundary of your structure. You define the support edges. Once you do that, you need to make sure your soap is dense enough, and then you can generate, this is a catenoid, so this line here is actually a catenary, and the surface of revolution becomes a catenoid. So this one is called catenoid. This one is a kind of saddle, but it's a shell, and I'm going to show you that the bridge was done using these boundary conditions. It looks like fabric, but this is soap bubble. The photograph resolution is not so good, but this is the one here at the bottom. They are all soap bubbles. Then we increase a little bit the scale, so we go here and we make a model done out of fabric, and then the final bridge. So let me explain you what the thing is. Imagine, I'm playing with a piece of fabric like this one. So what I can do is that I put it in a state of tension, all right? So I tie this in all the directions. And this is what happens in the models here at the bottom. So you see it's tied in 2, 4, 6, 8, 10, 12 points. But what's the real situation of the bridge? So the bridge has got a deck, and the deck is in compression. And then on the ground, again, there is a reaction, which is in compression. So the pure tension state becomes a state of compression only. So you see the inversion? So the bridge is actually designed according to that. So what happens is that also you design just one bay, and then you repeat it, change a little bit the proportions, and make the rhythm of the bridge. Is it clear enough so far, the way these things are designed? Yes? There are also other techniques which are, at the same time interesting, but also difficult to deal with. One is the use of pneumatic forms. So you can you take a membrane, you blow air in, and then you see what happens when you get this type of balloons. You define different boundary conditions, such as in this case, and then again you can get the shape of a shell. All these techniques generate structural form in a slightly different way. But there is also an architect who decided to use the same principle, not just to find form, but also to construct it. So he said, if I pour plaster on a small model, then I inflate that and I get a physical model. Why can't I pour concrete on it, and then I inflate it, and I design and construct a shell without using any scaffolds? And then he did that. And this is an Italian architect, Dante Bini, started that in 1964. Then he went to Columbia University, and he made a prototype over there, which went to the New York Times. And then the New South Wales State Department of Public Works decided to call him to design and construct school facilities. So basketball courts, multipurpose centers, libraries. Most of them are in New South Wales, but the technique was fast to construct. So it was able to build these type of structures in 13 to 14 days. So it's pretty fast. So you see here what happens. They place the reinforcing rods in a radial way within some springs just to keep them in position. So the springs have the same property of a bar chair. Then they pour concrete on the flat surface, so rather easy. And then they place a membrane on it to cover it. Of course, there was already a membrane underneath. There is also a concrete ring that keeps it in position. Then they blow air, just a 5 horsepower compressor, so not so much pressure. It takes 4 hours for inflation. Then you need to level the surface. And once it's done, that's what you get. Then that's the most fascinating part. You cut off the openings so that you can access the shell. And in 14 days, the building is ready. So it's really fascinating. And what is fascinating to me is that the way you find a structural form is also the way you construct the building. So the two things are actually the same. There is one last way, a little bit less sophisticated but interesting, to find structural form. And this was mainly diffused in Mid and South America. The idea of using analytical surfaces. It was also used by the Romans. So for instance, you take a sphere, or Utzon at the Sydney Opera House. You discretize a sphere, you can get some type of structural forms. You discretize, like in this case, you see here, this hyperbolic paraboloid. You trim it and you get a portion out of it, then a polar array. And this type of saddle is very similar to the minimal surface that you would get with a soap bubble. And if I take a section out of it, the arch I would get is very similar to a catenary. It's not that, but very similar. So if I don't want to play with models or I'm not sure how to do that, I can just work with geometry. And by means of geometry, I'm going to get something that is very close to the optimal one. So that's another way to do that. And I tell you, you can design very interesting structures even by doing that. This is one of the most fascinating by Felix Candela. Again, Google this name because Felix Candela has done so many interesting structures, and they're all done according to the principle of using analytical surfaces. The Sydney Opera House is another one, very similar. But can you believe that this is a composition of analytical surfaces? So this is a composition of 20 hyperbolic paraboloids and a set of there is a frame also that keeps them together. But I redid the geometry in Rhino, and that probably is a bit more understandable. So it's symmetric. So what you get out of it is that you divide it in, you can mirror it twice, and then you get these 4 hyperbolic paraboloids plus 1. Here the cover is in the middle. And then there is a frame of 14 bars that keeps it together. Then double mirror, and that's the structure. So it doesn't have to be boring just because you use some specific rules. You know the rule and you start composing. You play with that rule, and that's the interior. So again, the idea of bringing light in, because with discontinuous shells, you can't really have light coming from the top. So somehow you try to recreate these clerestory-like windows, right? Does it make sense to you? Have you ever seen these type of structures before? Never? So that's the construction, rather interesting because it was done, nothing was prefabricated. Everything was cast on site. So it's a little bit difficult to do that nowadays, but you know very well that hyperbolic paraboloids are ruled surfaces, so they can discretize by means of lines, so it's rather easy to place the reinforcing rods. So that's why that's also an interesting solution, and that's also why at the Sydney Opera House they decided to use the discretization of a sphere, because it was much simpler to construct. Otherwise they didn't know how to define the formworks, how to define the geometry, because that's the only way to use planar elements and discretize a continuous surface. But now let's talk about bridges. It's more interesting because these continuous surfaces let light in. In this case, Look at this. We've got already two families. Steel and glass. We are at the DG Bank in Berlin on the left. So this is the interior, designed by Gehry, but the roof was designed by Jörg Schleich. And on the right, Trio Gritschel. This is in the south of Italy, in Puglia, designed by Gritschel.it. They look similar to each other, but I'm going to show you that there are several differences. In this one, what happens? First of all, we've got triangles. Try to look at the geometry first. So what happens in this case is like having a piece of paper that you just bend a little bit and it takes that shape. So that's what happens. So in theory, you can get this type of triangulation on the planar surface, a set of triangles, then you deform, you bend that piece of paper, and you get that surface. Once you have that surface, you can build it this way. Why you're using triangles and not quads? You're using triangles because quads wouldn't be planar, because a plane is always defined by 3 points, and the fourth point would define a doubly curved surface. And can you imagine what's the price for this type of steel? It's very expensive. The ratio of planar glass to doubly curved glass is 1 to 10. So it's very important that you make sure that you always use planar glass, never doubly curved glass. When you see a project done with doubly curved glass, it means that it was a very expensive project. So we don't do that in general. It's a very specific and special stuff to do. But here, you see here that these triangles are done in order to avoid this problem. So what happens is that you generally discretize a diagrid first, so a set of diamonds, one diagonal, and then a second diagonal. So you see one diagonal here, and another diagonal there, and you get diamonds. And then bracing is done in the third direction. So these lines, which are parallel to the point of view, they're actually the bracing system. All right? British Museum, the British Museum, the Great Court of the British Museum in London is another example of this kind, because what happens, you see, everything is triangulated so that we make sure that everything, all the glass panels are actually planar. But what happens in this case is a very interesting example because look at the roof. There is a rectangular shape and then there is a circular shape inside. So it's an interesting architectural topic, the combination, how to blend a circle into a square. So that's the difficult part. So what happens is that this is the final geometry, but I can tell you there were so many studies about how to make these triangles. What is the geometry of these triangles? Well, the geometry of these triangles is defined first radially, so you just divide the boundary in a set of points, and then you make sure that they all converge to the center. And then from that you define some specific arches, which are, they're not catenaries. In this case, they've used a specific function to define an analytical surface, because it was done before 2000. So generally, they prefer to do that before 2000. And then after that, you see again the diamonds, the diagrid, and then the bracing is every second element, so that we get this view, all right? You see that the finesse is that the last element, we get rid of the bracing so that we have a clean triangle, and they're more homogeneous also in shape. So the design, again, is made of small details, and that's the interesting part. So when you look at these projects, first, try to think about the shape. Is that done through form finding, or is there another way to do so? And then the discretization. Discretization is the second part. So how did they get those triangles? So what was the design intent and the technique? And the way to build it also is rather difficult because, you know, these beams are actually going in all different directions. So what they did so many jigs to place them in position and define prefabricated sleeves. So you see there is a node with some sleeves, and then the beams are all planar and they are welded in place. So it's a fairly complicated project, but you try to prefabricate as soon as you, as long as you can, you try to prefabricate it. There are other situations in which the shape is completely freeform, but still we are keeping the same type of stuff. So you see here, this one is the Maizal shopping center in Frankfurt. So what happens here, the facade is completely planar. So until this point, we've got quads, so just diamonds. Then it becomes doubly curved, and the quads become triangles. And when we go inside, they're all triangles. Again, the thickness is rather reduced, so here we're talking about something that is less than 10 centimeters. And this one is done out of timber, but I can tell you that this is not real timber. This is glulam. So laminated timber is actually engineered timber, and it's very similar to the behavior of steel, because these elements, you see here, they are preformed. So they are already pre-bent, and they are connected exactly as steel is. So there is nothing to do with natural timber. So natural timber is another thing in terms of rituals. So this one is done by the same people who design steel and glass rituals. It's very difficult to do so. You know, 6 layers and all these type of joints, it's a project that nobody wants to do. Nobody wants to deal with that. It's too difficult. We also used it as a case study with the students at the master, and this was the only project which they weren't able to replicate because it was too complicated, even geometrically speaking. So I highly encourage you not to go this way if you can. Another example of freeform, when you want to simulate this vortex, maybe you want to make sure that your triangles are actually emphasizing the geometry. But I want to go faster because I have so many things to show you. Eden project in London, no, in the UK, close to London. In this case, what happens? We've got hexagons, and then there is a triangular bracing inside, but this is not glass. This is ETFE. So this is a lightweight cladding. Transparent. UV can pass through, so you need to use some protection when you are inside. You realize that only after you have been there for 2 hours. And an interesting thing is that you can also place shading devices on the top of it. So the shading devices can actually become an integral part of the design. This example is probably more interesting. So the Esplanade in Singapore. You see that there are 2 shells which are rather similar, but the position and the shape of the shading devices make sure that there are differences. So that's the design. So you see here, variety comes from that. So it's very interesting that also to notice that design in ritual construction is made of small details. So the shapes are rather simple. The shapes are always the same. But the design is made of construction and structural principles. So when you've done the shape, you have actually done nothing. It's just the beginning. The design has still to start. And when you achieve this result, then you're done with the design. It's not something you can delegate to someone else. This slide is just to show you what we spoke about in the lecture about reciprocal structures in timber. You see here the joints which are reciprocal, but this is a kind of ritual. So this is a kind of ritual as well. So you see that changing material, changing nodes, everything changes. The design is done of that. But the first timber ritual is the multi-halle in Mannheim. It's this one here. You don't see any timber from outside, but I can tell you that from the inside, this is the situation. This was done in the 70s, 1975, I think, to be precise. And what's the difference between this one and the one done out of steel? Well, first of all, we've got quads. So you see there are no triangles. Why that? You've probably realized that when you have a grid of quads, they can bend, they can fold, they can move. With triangles, you've got a stable structure because it's braced. This doesn't have to be braced because the way they do it, first they do the model, form finding. So you see here, there are these very small rings between elements so that they get this funicular shape. Then photographs, surveys, drawings, and then construction. But what they do, they start They start from a planar grid, and then they bend it, they push it, squeeze it, and lift it up to get the final shape. I'll show you later on a video on how to do that. But the way this was done is starting from a flat grid of quads. So that's interesting because, again, the design and construction are becoming close together. So they are exactly the same thing. There is a very complicated system in order to lift it up because it was very heavy. So there is a system of cranes from the outside, and then these scaffolds, which can be, extended according to the height of the building. The Dowlais Museum is another example of timber grid shell. Again, you see there are quads because these elements must be able to rotate, move, and bend. But the way it was done, it was not, let's say, the system which is called push-up. This is called pull-down. So you see there is a scaffold over here. This scaffold is because on the top of it, there was the flat grid, which was kept also in position and then pulled down using these props. So that was the way they did that. So there are two ways, to push it up and pull it down. We've also done this with the students to try to replicate it. And an interesting aspect of this project is that they really force the shape, because when you find the shape through form finding, you see that it's a bit less wavy than the original one, so they actually forced it to take a specific shape, which wasn't optimal, because they liked the wavy design. And another thing is that they increased and reduced the density of the grid according to the need. But the beginning is a flat grid. And you can do that with a physical model. So it's something you can replicate easily. Saville grid shell is the third example and the third and last construction technique so far. So the way they've done it, this was very, very thick, so they couldn't bend it on site. What they did, they did 2 layers, and then they bent it, and then they built the other 2 layers on the top of it. What you see here, they are shear blocks, and there is no bracing yet. So you see 1 layer of lats, and the orthogonal one here, with the shear blocks on top, and then they built the 3rd and the 4th layer on site, and then cladding. But I'm going to talk to you now about gridshell.it. So you see that when you've got this grid of quads, you can fold it. So the first idea was that gridshell.it in Italy was born because the idea was to make these kind of prefabricated slabs that you can fold, put on the truck, and bring on site. Then you unfold it, and then you just place it over there. But playing with that, they realized that you can actually bend this and put it into shape, into structural form. So what they did was to start playing with this type of property of the material, and they started designing grid shells. There are also geometrical ways to do so, but I'm not going to through that now. So what they did was to make these physical models. You see that from a flat surface, they develop a 3-dimensional structure, and then with the 3D scanner, they scanned the position of the nodes to make sure that they were able to make a CAD drawing. And that was the beginning. And the technique to lift it up was to use a system of ropes. You remember the block and tackle of the second lecture? So that's the system. There are a set of ropes and pulleys to pull it up in that direction. But what I want to show you is that you see the starting point, then the first push, second one, and I'm also showing you a short video of the construction of the moduli, and then from the moduli you build a flat grid. So this is about 1 to 2 days of work. And then having done that, you place the system of ropes and you push it up, and it's probably another day of work. The third thing you need to do is to add the bracing system. Of course, you need to pull it a little bit beforehand, and then you're ready to go. And that's something you would replicate also with a physical model. So the way you build it is the same way you design it. That's the interesting part of it. You see, now it's still a bit flat on the top, so they still need to push it a bit more. Another difficult aspect of it is that you never know exactly when the shape is done, because you have no way to survey it. I mean, there are ways, but more recently. Okay, let's go to another project, more interesting. So this one is more completed. Again, it's in the south of Italy. After the first experiments, Scritcher.it was commissioned to do a few projects of this kind. This is for a restaurant and, let's say, bed and breakfast restaurant in the south of Italy. So what they did was to make this type of roof for the open part of it. So here is the structure, and you see in this case it's a bit more freeform, so the edges are never points, they're always kind of lines, and it's in part attached to the wall and connected to the roof, and in part attached to the ground. There is also a little bit of claddings done with, you know, like flooring elements. But in this case, they decided to go digitally. So what they did is to design it and simulate it numerically. So not experimentally, but numerically. So there are tools now with Grasshopper and Kangaroo. There is a tool, and there are also other external tools that allow you to simulate physical phenomena. So what they do, you have some prescribed displacements, and you know what the shape of your flat grid is. Out of that, you get this Rhino geometry. All right? So, and the computer simulates for you the steps. And you can also calculate exactly where the structure is most stressed and when it's going to break. So the red is generally bad, and blue means generally good. So you see here some phases. In this case, they couldn't realize moduli. They had to do it in place. So they just did a first modulus over here, and then all the other elements were placed one by one. And I'm showing you a small video, not a very good resolution, but you see the moduli are actually built one on top of the other, so to make it easier. And then they started at night to build the first part connected to the wall, because they found very expensive to make scaffolds outside that area. So they just wanted to make sure that the scaffold would never go out of this fence. So you see there is only one scaffold there, and they build the lads one by one. And they bend them in shape. Another interesting thing is that you see that the shape changes at every step. There was also kind of soundtrack, but I removed that just to make sure that it doesn't distract you. So you see here that the scaffold actually doesn't go outside unless for this small one there, because it was required, and it's almost completed. I think, as far as I know, this took about 2-3 weeks, probably 3. But let me go to the final one. So that's the final product. And I really recommend you to go to the website Grischer.it, or you can also go on ResearchGate and find their articles, and they'll show all the projects they've done. Again, a more recent one. This is about 100 square meters of roof. So you see there are the quads which allow the structure to move, and then there is bracing everywhere at the end. This is the Faculty of Architecture in Naples. It was done by 2 master students who developed a tool with Kangaroo to design these shapes, so not to do it by means of a physical model, but to do it numerically. And then Rhinoceros, Grasshopper, Kangaroo for the form-finding part, so the physics, and Caramba is a tool, affinity element analysis, to run the structural calculation. But I recommend you to go to this website, ResearchGate. You can download the articles for free. You can read them. This is the final structure, and I'm going to show you the video, but I need to go outside of that because the video is rather heavy and was creating a bit of problems. So they did a tool that allowed them to start from any flat grid and then define the boundary conditions and to trim it according to what they wanted. So you see here that there is the possibility to trim the structure the way you want it. Then they started with other students to build the flat modeling. and then to lift it up. In this case, I think it's worth noticing that there are never cranes. So everything is done just using props, struts, but no cranes at all. So the idea is also self-construction. So no complicated machines, but always the use of simple machines. So here you see an example in which you can actually change the boundary conditions and you get straight away a numerical simulation of what the physical model would be. And for who doesn't know, this is the interface of Grasshopper and Rhinoceros. So it's like AutoCAD. But there is a parametric tool, Grasshopper, that allows you to define these parametric relationships and to simulate physical phenomena. I think I'll just flip through and go to the next slide. So we'll go a bit faster. Another example, just I wanted to show you that because you can also transport them. So you just make sure that they're actually fixed on the ground so that there are ties. That's the way to do the modeling. So you see you build the modeling one on top of the other so that you make sure that you are consistent and faster in doing that. And these are the type of shop drawings you do before that. So you have this drawing in front of you, and then with colors you recognize the type of LUT you need to put in place. Then they're also shifted so that the connections are done not on a single line, which could break. That's how they look. So this is about 25 mil by 50 mil. So that's the cross section. This is the flat surface. In this case, there is no crane, but there is a scaffold which is used to lift it up. Second step. Yes, at the third step, you probably noticed that this part of the scaffold was dismantled and reconstructed because otherwise you couldn't lift it up. And then even further. And this is not the final one, but almost. So you see there is no bracing yet, but that's the way to do that. This is the new pavilion at the University of Naples. And we also did one in Australia here, so we did it last year. I don't remember if I showed you this video, but I'm going to show you the video anyway. So here is a slideshow, and then there is also a time lapse of the construction we did here in Melbourne. You probably recognize the facilities of the previous building, 757 Swanston Street. So what happens is that, again, you start from the flat moduly. So this is day one. And then from the flat moduly, then you start pulling it up with the system of block and tackle. And now there is the time frame. Time lapse, sorry. This was rather fast. It was actually, we did it in 5 days. So not so bad. Of course, you need to design it before, but the construction took 4 to 5 days. It was a very small one, so it's 48 square meters. And you can't do it all at once because, you know, it needs to, sometimes the timber needs to relax a little bit. You can't bend it all at once, otherwise you would risk to break a few LUTs. And the reason why we stopped is also because we broke a couple at the corner, so we needed to replace them in play. And this is the second part. You see there are always these props to keep it in position in the meanwhile. And the system of ropes is here underneath. Then they're going to all the wings. And these are a few images of the design and the final construction. All right, so short break, back in 10 minutes. Ready to start? We're going to be very quick in the second part, I hope. But the point of the second part is, okay, we've talked about optimal structural forms. But what happens now when we want to deal with forms which are completely free-form, or maybe they are inspired by organic shapes? So if you look at these two examples, how can you achieve this result? You can't do it by means of fault finding, so you need to do something else. And in this case, it's the same. You probably know this project is very recent. It's a crematorium in Japan, designed by Toyo Ito, together with the engineer Mutsuru Sasaki. And you see, this is a kind of a flying carpet, but the real point of it is that if I want to hang a piece of fabric, I can't get this shape. So it cannot be an optimal shape. It has to be a suboptimal shape, which I can obtain by means of mathematical optimization. So it's another process. And this is the definition of this process. I mean, again, these are all definitions I'm doing myself, but somehow it's a synthesis of what I could find around. So mathematical optimization is the process, so again, it's another process, in which we search for optimal solutions to a problem from among a series of possible candidates. And the way we do that is on the basis of one or more selection criteria. So what we do, we pick a problem, then we define a set of candidates to the problem, then we pick a selection criterion, let's say the tallest person in the class, and then mathematical optimization looks for the optimal, but also all the suboptimal solutions. So this means that we are able to choose something which is not exactly the optimal one. Form finding aims to find the best. Optimization aims to explore solutions as give me the possibility to decide what I'd like to do. So in the case of the crematorium, that was the beginning. So the beginning was an architect intention. So I want to do it this way. I've got a series of columns positioned here and there, and that's the wavy shape I want to do. The first thing to do is to transform this drawing into a parametric drawing. And the way to do so is using NURB surfaces. NURB surfaces come from Bézier surfaces and curves. Bézier was an engineer working at Renault, so he was supporting car designers and the automotive industry. They had problems because the way they used to design was by hand or by doing mock-ups. And using Bézier curves and surfaces, they were actually able to have some parametric drawings which allow them to modify them in real time. B-splines, you know that because in CAD we use that. And even when we go to the 3D version of the NURB surfaces, we've got a very high local control. So I've got control points which define a surface, and if I push this down or pull that in that way, you see that I have local control on the surface, and this is very good because it's a parametrization that helps designers. So in Rhino or in 3D Max or Maya, I can actually just move the points and make sure that I act locally on the geometry I'm working on. So that was a revolution in the 60s. And it actually comes from the study of mathematicians of the 19th century, which was a useless study, but it became useful now that we've got computers. Another thing you can do is you can reparameterize the same surface. So you can describe these by means of 1, 2, 3, 4, 9, 6, 9 control points, but you can also do it by means of more control points. And this is a sample, just a sample of how you could describe the shape of that crematorium, but parametrically speaking. So I think you can already predict what it's going to be. It's going to happen that I'd like to move these points and make sure that the shape I get, it still belongs to the idea of the flying carpet, but it's structurally better than the first one I pick. So what I'll do, I'll define boundary conditions. Remember we talked before about boundary conditions. So boundary conditions are the columns, the position of the columns, and the height of the columns. But if I want to understand which one is the best shape, I have to tell the computer among which set of candidates. So I have to say, for instance, I'd like to move just the z coordinates of the points, and maybe let's say between 3 to 10 meters height. So I need to provide a variety. All right? Let me show you that straight away in Rhino. So what happens here is that, So this is the crematorium. So you see here, I've got the top view, and I've also got a perspective view. This is a sample of the representation of that crematorium using a mesh. And what I'd like to do, I'd like to make sure that I'm able to control the coordinates of these points, you see, individually, so that I'm changing. You see here, I'm changing something. And I'm able straight away to understand what happens in terms of structural behavior. But I don't want to do that manually. It would take ages to explore all the different shapes. So there are tools to do that automatically. And I'd like to see at the same time front view, perspective view, and also top view. And I'm going to show you how these algorithms work. The way they work is that they start exploring, you see, all the possible variations of the system, and they're going to tell me which one is going to be the best. But at the same time, they're going to tell me also how the others are ranked in the, in the final list, so that I'm able to explore rather than find. So that's a design tool which is more powerful than for finding. Of course, it will take a while, so it probably take, I don't know, 24 to 48 hours to make sure you get a good set of candidates to look at. But I'm sure that at the moment we can probably stop it before. But what happens here is that I can also see straight away in this window, for instance, what is the maximum displacement of the structure and where are the weakest points. And you see straight away what the geometry is. And if I want to change some values, some specific values, I can directly go on a slider and change it. And I affect straight away the structural behavior of my shell. So that's the way nowadays these things are designed. When I did this the first time, there was no Grasshopper, so it was done in another interface. It was in 2006, 2007. But I replicated this for the students here. But that's the way these type of structures are drawn, optimized, and designed. There is still a problem of construction, but that's another thing. So, and this is the way I just summarized the results for you. So, it's like when you go to, there is a TV show about cooking and kitchen. So they start cooking, and then at the end they show you the final product. And this is the final product. So you see here there are very weak points, the three edges, and also here in the middle, in the span. And then it starts improving until this generation. But somehow, if you look at the shapes I get, they all belong to my own idea. So my idea is that I want this type of flying carpet. All right? So let me show you that also from the historical case studies, you can use mathematical optimization to replicate them. So you've seen this church before. The original sketches were about the God tent, or you see this one, the God tent, the Möbius ring, and also combining hypershells together. So it's possible to make sure that you replicate that in a contemporary way using optimization. So you take 1/4 of the church out of that, and this quarter you make sure that the 8 points of the frame can be moved within a certain domain. And then you calculate the structural behavior so that you get a family of shapes from which you can select from. So its form finding is, let's say, the way it was designed, and mathematical optimization is a way in which we can design it nowadays. There is no better or worse, but it's just two different ways. And I'm going to show you a video also of that. So that's how the computer actually generates all the different possibilities that you can have and finds for you the best, but it also allows you to explore different possible variations. So it's rather interesting that now the focus is not on combining and composing things. Now the focus is on understanding what to do of the solutions, because you get so many solutions that you need to understand how to read them, how to interpret the results. So it's not a matter of finding variations, it's a matter of interpreting variations. Because we get so many solutions that we need to look at them carefully. And this is some of the possible bad ones that become, progressively better, and these are among the best ones, but they're all different from one another. So still I'm able to work with them and then design further. And, I can group families of solutions. There was a book, 1984, The Blind Watchmaker. It's a book about biology and a book about the idea of mutations in natural systems, in the evolution of natural systems. And that's the way Dawkins used to represent his shapes. And there are some similarities in the way we are doing this kind of metaheuristic study nowadays. So we explore different variations and then we group them. And then let's say we kill the worst one. And then we let the others live and progress. And by iteration after iteration, we go to the best ones. So another type of optimization, not everything is about structures, but there are also optimizations which are done according to acoustic criteria, for instance. So what I'm going to show you is that the way you can actually affect acoustic is generally using some panels which can reflect or absorb light, and you can add extra panels to the volume you already have, such as in this case. So this is the hall of the University of Caracas by Carlos Raúl Villanueva, 1952, and Alvar Aalto on the right. So the geometry of the ceiling is directly the way to manage acoustics. But what's the way to evaluate acoustics? Because we need to find also a tool to assess it. So the way to do that is that we have an omnidirectional source, and then we launch a set of rays. So we just trace different rays according to a defined angle. And then we evaluate the distribution of these rays according to the third order of reflection on the sitting area. And then we try, by means of an algorithm that I'm going to show you in a video straight away, how this situation of non-uniformity, like you see that the guys who are sitting closer to the stage get most of the rays, and the others on the back are not very homogeneous. And then you can actually optimize that to get a better situation. Now let me show you a thesis that has been developed last year at the University of Naples. I don't know why it takes so much time to develop. Yeah. All right, so this is a thesis developed by master students, and the idea was to make an acoustic shell for open-air concerts, so without amplifiers and without extra tools. It's very difficult to play classical music outdoor, and it's already the fourth year in a row that they are working on that, and this is the work of the final thesis. So first in Grasshopper they define the way to trace the rays. Then the second thing they study is how to manage obstacles. So there is a first phase in understanding performance and also the way in which you parameterize the system. And then there is a second phase in which you actually launch the optimization. And the optimization, you see, you're launching all the rays and you try to understand after 3 orders of reflections what type of uniformity you get on the sitting area. So here you see the geometry in Rhino and all the different parameters which you can vary, so which are actually just the shape and the orientation of the panels. You also see sometimes a little bit of the construction. Generally, theses are running a bit longer in Italy, maybe for 1 year, 1.5 years. So it's like 3 semesters of thesis. Yes, and now you see here the optimization. So you see all the different possible variations of the systems and also how the sitting area is affected by that. So you can actually use these tools to explore things, not just to, just to optimize in the mathematical term, mathematical meaning of the term, but also to understand the problem. So the most important thing of that is that they change the way you think and the way you design. And that's the final construction which is going to be realized. It's a very difficult construction because it's rather heavy, so without crane is a bit problematic. All right, let's go back to the slides. I want to show you one last problem you can solve by means of optimization, and then I'll let you go. So the problem I can solve by means of optimization is called the planarity. Why planarity? You remember before we spoke about the idea of triangulation. So of course, you can triangulate any type of form, so you can discretize something continuous. But if I want to realize something like that, this one at the bottom, you see there are quads. Bracing is done by means of steel wires, so there are no triangles. And how can I make sure that these quads are actually planar? There are two ways. First is geometrical. So I have an idea of translating curves. Look at this one. I've got a generated curve and a directed curve. I translate them, and the geometry I get is actually planar by definition. I can also translate and scale curves. This is the train station in Berlin, it's done in this way. And following these simple rules, I make sure that the quads I get are always planar. Well, on the one end it's fine, but on the other end it's quite constraining. The Hippo house was done in this way, but it's still a very interesting project because the way it was developed is by translating curves and then trim the surfaces you get in the shape of a circle, so that you get these two circles over here, 1 and 2, and then there is a kind of fillet in the middle, so that the final shape looks like that, but the generative surfaces were actually these ones, 1 and 2. And you can do that in Rhino rather easily, but somehow we are very constrained by this idea of translating and scaling. If you want to design something that is a bit more, let's say, engaging than this very flat barrel vault, then you have to do the same stuff by means of mathematical optimization. So let's say you have a free-form surface like that. You discretize it, and what you get is this problem. This face is not planar, because you see there is this divergence of planarity. So what you can do, by means of mathematical optimization, you get that divergence, and you make sure that you minimize it to 0 by changing a little bit the shape. And you can do that again in Rhino. And I want to show you how to do that. So now, look at this file. You see, this is I don't know, it's a kind of snake, something that I drew just in 5 minutes just to make an example. So you see here, this shape is generated in this way. So there are 3 curves, and then these curves are actually, see here there are lofted together to get a surface, but I made sure that I'm able to modify the height and the position of these elements, and also x and y coordinates. You see that it changes over here. X and y coordinates are allowed to move, so that I have a set of parameters that allow me to change the shape according to the behavior. I have another tool which calculates planarity. So with this tool I understand that the green ones are a bit below my expectation, and the red ones are a bit above, and the yellow ones are fine. But again, by means of this tool here, I can make sure that I solve the planarity issue by changing slightly the position of. And if you wait 15, 30, 45, probably 1 hour, you will see that the tool will find one solution for you, or probably more solutions. So this problem, let's say, is not a problem anymore. So we can design whatever shape we want, and then we are able to, to look backwards and optimize it later on. So there are ways, such as form finding, to make sure that what you do is intrinsically good because of the method you have used to design, and mathematical optimization that let you design whatever you want because then you have a method to solve the problem you define yourself. So these are the two different possibilities. Now I'll stop it because I don't want to see the final result. But this was, for instance, the way we designed this roof here on the right, which was not realized, but we started from a free-form surface, and then after that we decided to optimize it. And of course we already knew that a few of these couldn't be completely optimized, but if you can get at least to 70–80% of the result, that's good. So what I want to show you now is the National Maritime Museum. The National Maritime Museum is a hybrid. So what happens here, I've got this square court, and there were the sea charts of the 16th and 17th century. They were inspired by that. So the way they generated the shape of the Critchell is not by triangulation, but it's according to another rule. So you take a center, and then you draw 16 lines, so a polar array of lines. Then you divide the circle in 16 parts, and you copy and paste that array 16 times. What you get is this mess of lines. You extend them, and you trim them with a square. And that's the shape of the roof of the National Maritime Museum in Amsterdam. Well, so far, we're not talking about planarization, but the shapes we get out of it is that, we've got a few triangles, the blue one. The cyan ones are quads, so they need to be optimized. These ones are pentagons, and the ones on the left, they are hexagons. So out of that, I think we have less than 1/5 of the surface which is already working because it's done on triangles. The other ones are shapes, which are completely useless because they're doubly curved in the way they are. So this is something that you can do by means of form finding first, and then you need to optimize it in order to solve the planarity issue. So it's a fairly complicated project. There is no time to show that in Rhino. I'll do it next time. But I want to show you a few images of the projects done by the students at the master's level. For instance, this one. This is a typical project based on form finding. So what happens here? It happens that this student realized that you can hang a piece of fabric, and then you can change the position of the suspension points, release some of them. You can start from a square, or you can start from a triangle. And then you compose them together. And then from that you define a pattern, also to allow light in, to let light in. And that's the type of temporary shelter that this student designed. You see here that there is also a type of light study in order to make sure that the size of the openings is done according to that, in order to manage and control the light. Probably the footings are a bit optimistic, but that was not the issue of the studio. Physical models are generally done with 3D printed elements and then timber dowels to connect them together. This is a case of post-formed timber Critchell. So this student started, you see, from this node and a flat surface, and then numerically, so she didn't draw by hand all these lines, she did it automatically. She did a physical model and all the shop drawings. Another example, in this case, the student decided to use optimization, so this is not form finding, because she wanted to be able to manage the geometry at certain points, which are the red ones, and to make sure that the geometry is also fixed at other points, which are the cyan ones. So you see here what happens. She started from this behavior and went to this one. So there is not really a strong design intent, but just the idea that I've already something in mind, I just want to make sure it works a bit better. This is another student. Again, the idea was already there, so I have this idea of this kind of butterfly. I just want to make sure that it's a bit
more inflated, and the behavior is a bit, more related to the idea of the membrane action. So what happens is that stage 1 we are here, and then by means of optimization we get closer to the best result. Again, the nodes are 3D printed because they're all different, and the elements are standardized. So you see also the physical model is a kind of understanding the construction. So the physical model has to be done according to that. Another example of optimization, so I start from this shape and I say, all right, I give you the possibility to change the size of some rings of this shape, but also the wave of the boundary conditions. And from this starting point, we get a little bit better, but still the design intent was there, so I'm just slightly improving. We could talk about form improvement. This is about light again, and I'm going to show you another project of the last year. Well, it's rather complex when you deal with shells. The problem is that a shell is a roof, but at the same time it becomes a wall sometimes. And when you have openings, then it highly affects what happens underneath, because the height of the ceiling changes. So somehow the project is the roof. Structure becomes architecture. And it's at the same time a limit, because it's a strong limit, but it's also the potential. So it's very good to think always three-dimensionally, never in terms of plan and sections. It's a bit more difficult to think in that terms. Plan and sections is always the best way to go, but in this case, they can be a little bit constraining. So you need to make sure that you have the right tool to think always three-dimensionally. And again, we are talking about optimization. So we define in plan view the position of some specific openings and the boundary conditions, and then we make sure that we want some waves, and by means of a few iterations we actually improve the behavior of a little bit. When we have continuous shells, we can also make physical models which are done in a very similar way. So we can use plaster, we can pour plaster on a foam that we have already shaped by means of a CNC. And that's the way to go. So you place these, they are just insulation panels, so just foam. And by means of the CNC you get this shape first, then you pour plaster on it, and then on the top you go again to mill the shape with the CNC, and then you get something like that. You wait probably 2-3 days that it dries, and then you can take it out, and you get the shell. So it's a very similar process to what you would do with concrete. So that's the way to make a physical model of that. Also recently we've done a visiting studio in Nanjing, China, and what we did in that case was all about timber. So in that case it's a bit easier because you just cut some stripes of boxboard, mountboard, plywood, and then you start playing with that. You see, the first thing they do, they define a grid of quotes. Once they have the grid of quotes, then they start playing, folding, bending, and they define a few different shapes. For instance, this one was done at the same time by means of a physical model, paper first, and then they play with a steel mesh, and then they do it out of boxboard. Then they also do it digitally to make sure that the shape is completely controlled. They run a structural analysis, they go back to the physical model. So it's a forth and back. I don't want to say that now we need to use only numerical tools. Now we need to use both. And we need to use both and go forth and back and have a continuous feedback from physical and numerical tools. And that's it for now. If you have any questions so far, I know that this is a very different topic from what you've seen in the previous lectures, but I'm happy to get questions also by email if you feel. And I'll meet you in 2 weeks. There will be Chris Jensen talking about energy in housing. Any questions? No? Pardon? Sorry, it's wrong. It's Friday. Friday, don't come Wednesday.